Okay, so people are still joining. Okay, we'll just begin with the class, and I think maybe in a couple of minutes everybody else can join. Started the recording. We are looking at antennas and radiating systems. We have done all like more than half of the course. Today we'll look at module 7, transmit and receive systems. In the previous class, we were looking at receiving antennas, and we covered internal impedance and directional pattern. And in the class before the previous class and the previous class, we looked at effective area and backscatter cross section. Today, we will cover both these topics: phase transmission, the radar equation, and wave propagation errors. This is a very small part. And from the next class, we'll start looking at the individual antennas and finally aperture radiators. So we are, I think, this is our 8th class. Yeah, so we are here in like 1170, 11.7, and then we'll look at these types of antennas and aperture radiators. And if we have time, we'll do a couple of maybe question Q&A classes at the end. So I'm yeah, looking forward to having a total of 12 classes, I think. Let's see. So yeah, so the last class we covered these topics. Today we'll cover transmit receive systems with this transmission equation, very important. Radar equation comes from this, and then wave propagation near Earth surface. So in the preceding sections, let me switch to 10. In the preceding sections, we discussed the concept of effective area for receiving antennas and backscatter cross section for scattering objects. Okay, let me just do this. Okay, I hope this. Let me just put a message on the WhatsApp group saying that to use this particular link instead of the one which is shared in the meeting. Okay, so I just pasted it. Okay, so I wrote in the WhatsApp group. Okay, back to the class. So for receiving antennas, we had effective area, and the previous class we saw backscatter cross section for uh, scattering objects. Okay, and so now we'll examine power transmission relation between transmitting and receiving antennas. So the first case we had just a transmitter. The second case, and then we had this receivers, and then we had some objects which were neither transmitter receiver; they were just scattering. And now we look at a system where we have transmitter and a receiver, and so they will send some signals, some will be reflected back, uh, something like that. And in so this will be for the frizz where we have sorry frizz where we have a transmit antenna and a receiving antenna. And then in the radar equation, we'll have a transmit antenna, a receiving antenna, and maybe some object from where it is scattered. So when we use the same antenna for transmitting short pulses of radiation and then for receiving them after they have been reflected, scattered back by a target, the transmit receive system is a radar. It is a special case, and the measurement of the time elapsed between the transmitted pulse and the received pulse determines the distance r of the target. So um, let's just say we are using the same transmitter here, and then we have some target or object here. So we send some signal, we send a pulse, it is reflected back, and this total thing will take some delta t time, and we know the frequency, and so we can do some math and calculate the distance between the two objects if it is r. So so the relation delta t is equals to 2r by c. So know the velocity of the wave, which is c, and so this gives us the total time difference delta t. So we have this relation, and so to find out this r, we can measure the t, and we know c. If the transmission path between the transmitting and receiving antennas is near the Earth's surface, the effects of the conducting Earth must be considered. So this is in this case, so this is just an overview of what we'll look at today. So if this is the case for when if the propagation is near Earth, so let's say this is Earth, and we have our antenna at some distance like this, and we have our receiver at some distance like this. Sorry, like this. So this is one way where the wave could travel. The other way could be it reflects back from the Earth's surface and then reaches the air. Uh, so just taking a simple two ray model, we should calculate the total electric field that will be reaching here. Okay. So and we shall also discuss. So this thing will discuss. So the actual case, the Earth is not flat, right? It is spherical. So this becomes more complex, but we will discuss it just for a flat surface case. Sorry about that. From the previous classes, we had these two formulas for directive gain and the relation between the power transmitted and power received at the load, which was dependent upon the effective area of the receiver and gain of the transmitter. Just a second. Okay. So let us consider a communication circuit between stations 1 and 2, where we have antennas whose effective areas are AE1 and AE2. So there is some, let's say, station 1, which has an antenna and its effective area is AE1. And then there is another station 2 and its area is AE2. And they are separated by a distance R. We wish to find the relationship between the transmitted and the received powers, that is PT and PL. PL is basically the power received at the load of the receiving circuit. So let PL and PT be the received and transmitted powers respectively. So we'll combine these two equations 1113 and 1121, and this gives us the following relation. So we are taking this relationship, and over here we will substitute the expression for GD1 from this. So we get AE by 2 upon 4 pi r square, 4 pi AE1 by lambda square. So we can rearrange and write it like this. So the receive power upon the transmit power is equals to the effective area of the transmitter, effective times the effective area of the receiver, upon the distance, square of the distance, and the square of the wavelength. Okay. And this particular relationship is known as the Friis transmission formula. So this is the popular Friis transmission formula used to solve many numericals and problems and in your exams or in real life. And now, so a definition would be, for a given transmitted power is PT. The receive power, which is PL, is the product of the effective areas of the transmitting and receiving antennas. So this is the product of the transmitting and effective area of the transmitting and receiving antennas, and is inversely proportional to the square of the product of the distance of separation and the wavelength square. So we can write it like this, like C power is equals to AE1 times AE2 divided by R into lambda whole square. Product square of the product of the distance and the uh, wavelength of operation. So noting this particular equation 11,121, we may also write the Friis transmission formula in an alternative form, which is the received power is equals to the product of the directive gains of the transmit and receive antennas times the square of the wavelength and divided by the uh, by 4 pi r square, where r is the separation. So this is the other way. So instead of substituting g over the gain over here, we substituted the value of effective area. So this is another relation, but we have to note that the receive power PL over here and 132, they assume a matched condition, that is all the power which was received at the receiving antenna was all of it was delivered to the load. So if there is any mismatch over here, in that case, not all the received power would be received. So then we will have to modify this 131 and 132 to incorporate the mismatch as well. So over here there is no mismatch. And yeah, and also disregards the power which is dissipated in the antenna itself. So just in case if your antenna is not efficient, so just for example, if it captures 1 watt of power and it transmits only 0.5 watts to the load, so the antenna implies that the antenna has losses, and this particular relation does not consider the losses in antenna as well. So there is losses due to the antenna, which are not been considered, and there could also be losses due to mismatch over here, uh, which has not been considered. Uh, so just in case if you're trying to solve a problem and you see that there is some only so antenna has a certain percent of efficiency, or there is some mismatch, we have to consider them into account as well. And from equation 131, this equation over here, we see that that for a given transmitted power, the received power increases as the square of the operating frequency. Uh, so this is the wavelength over here. So it decreases with the square of the operating wavelength, which implies it is this PL upon PT is proportional to f square, square of the operating frequency. So I'll pause over here. If there are any questions, so I'll be away from the screen for a couple of minutes. If there are questions, you can type in chat or ask them when I'm back. Guys, I don't see questions in chat. Um, if there are no questions, like, are there any questions? Okay, so just quickly recapping stuff. Um, so we in the previous class we had seen how we had seen the derivation of this equation 11113, the power received versus the power transmitted, and this relationship between the relative gain and the effective area. Using these two, we have derived uh, the Frisch transmission formula over here, and we have also written another form of the Frisch transmission formula over here. So that's what we discussed now. So if there are no questions, we'll continue. So we derived 11131 and 11132. Now, uh, and uh, and we also discussed that this is the case when uh, we assume matched condition and we disregard the disregard the dissipation of power in the antenna itself, and also that the this received power is directly proportional. The received power PL is directly proportional to the square of the frequency. Uh, but there is a catch. At progressively increasing frequencies, the transmitted power is limited by the available technology. So, so if we increase the frequency, the our so we won't be able to increase uh, like we won't be able to keep the transmitted power at the same value. So so at for higher frequencies, we'll have to reduce the transmitted power. So which implies so this is also the power at the load is also proportional to uh, the transmitted power as well, right? So, but we if we keep increasing this frequency, we will not be able to keep this transmit power constant. We'll have to reduce this as well. Um, and the minimum detectable power over electromagnetic noise ratios also increases. So this so this statement means that uh, the antenna at the receiving end, right? So we had a transmitting uh, station one and sorry, station one, and then we had a another station which is acting as a receiver. So in the power which can be detected by this uh, antenna, there's a minimum power which has to reach from the transmitter. This P minimum is also this also reduces uh, as we so the power, the minimum power which this particular antenna can detect, it also reduces at higher frequencies because the noise flow, the amount of electromagnetic noise, the EM noise at higher frequencies, it also increases. So if you keep increasing your frequency, the power of noise will also increase at at the higher frequencies, which implies you will need more power in the signal at that particular frequency. But again, we are limited by the amount of power which can which we can send through the transmitter. So I hope like this was clear. If there are questions in this, you can ask them now. Okay, so I'll repeat this again. Um, we are limited by the power. Uh, this PT uh, is we cannot scale. We cannot keep it as high for higher frequencies as we can do it for lower frequencies. So we are limited in the power which we can send at higher frequencies, which imply, and also the minimum power which has to be which has to be received at the receiver also reduces. So uh, we need this implies we need higher power at higher frequencies, but again we are limited by the amount of power which can send at higher frequency. So hence it does not mean that for receiving higher power at the load we can just uh, randomly increase this particular frequency over here and we will have better communication system. We cannot arbitrarily increase this frequency or keep it constant at the higher frequencies. Also, another catch is it is incorrect to conclude from this 132 that uh, receive power increases as the square of the wavelength, uh, because if you see from this equation, it looks like PL increases with lambda, but we have seen that PL actually increases with the frequency, uh, and so this gives a false impression because for for smaller wavelength, this gain reduces. So this gain, this GD1, okay, as seen from this expression, this GD1 reduces for uh, say, yeah, for higher wavelengths, and this implies that the power received is not directly proportional to the square of the wave. So to make sure that while like writing relations, yeah, you use this equation 11131 and not 11132. So it gives a false impression that the received power is proportional to the square of the wavelength. So now we can consider radar system that uses the same antenna for transmitting short pulses of time harmonic radiation and for receiving the energy scattered from the target. So now instead of again back to the previous problem where we do not have the second antenna, instead we have a scattering object. There is an object which when receives a wave scatters it in different directions isotropically, or it may not be isotropic. For a transmitted power PT, and the power density at the target at a distance r away can be so this expression can be given as PT upon 4 pi r square GDA. So this is the this PAV is the power. So example, we had our antenna over here. We sent some power PT over here, and then this by reaching this particular object, the power density over here is given as PAV. So PAV is given by this relationship, and then so in this particular case, uh, let's say the power which has been transmitted to this object uh, be written as PT is this small this PT, so this script PT is equals to PT upon 4 pi r square into GD, and GD is the directive gain of the antenna in the direction of the target. So this is the antenna in the direction of the target. It has GD, and we are sending in PT power P small t, and then P script T is the power which is received over here at the object. Okay. Um, so script PT is the power which has been received by the object, and this PT is the power which has been transmitted. Now, if sigma Bs is the backscatter or the radar cross section of the target, the equivalent power that is scattered isotrope, and this the equivalent power which is scattered isotropically is sigma Bs into script PT, which results in a power density at the antenna of this relation. So what we are trying to do is we have a transmitting antenna over here, and we send PT power. It travels to the object over here, and we receive script PT power over here, and then this it scatters sigma BS PT power, right? So it is scattering sigma BS PT power, and then this is reflected back to the transmitter. So back to the transmitter, the power which is received, so it is scattering sigma BS script PT power, and now this sigma BS script PT power when received back at the transmitter is sigma BS script PT upon 4 pi r square. So this is the power which is received back to the antenna if it's transmitting PT power. Now we can write this expression in terms of the transmitted power. So AE is the effective area of this antenna. So AE is the effective area, and so this is the relationship. So the power which is again back received back over here, and we are writing this again as PL. So PL is the power which is received back over here. AE is the from the so yeah. So AE is the effective area of the antenna. Sigma BS is uh, scatter the radar cross section. PT is the power over here, and 4 pi r square. Now substituting this script PT in terms of the regular PT, so AE sigma BS, the effective area, the radar cross section, the transmitted power, uh, again fourth power of this distance of separation, and the gain of the directive and the directive gain of the antenna. So rearranging this expression over here um, by using the expression 1 to 1, what was that? Yeah, we have the all the expression, right? Okay, substituting AE in terms of uh, GD, right? We have this relationship uh, that GD is equals to um, something this K times AE, and this K was something by lambda upon 4 pi, something this expression was there, right? So, so using that in 1134, we get this expression. So there is the ratio of the receive power versus transmitted power. Now, in this case, when instead of having a receiving antenna, we have a scatterer. So we have the radar cross section of the scatterer, this wavelength, both power of the distance of separation, and the directive gain of the antenna. Now, this is known as the radar equation. And in terms of the antenna effective area, instead of the directive gain, we can write this equation as uh, radar cross section upon 4 pi times the square of effective area upon lambda, the, the wavelength, and the distance of separation, and this is and the square of the distance of separation. So this entire thing is uh, whole squared. So this is the both of them are the radar equations. Uh, And because the radar signals have to make round trips from the antenna to the target and then back to the antenna, that's seen over here. We send the signal to r distance, and then it travels back again to r distance. So the receive power becomes inversely proportional to the fourth power of the distance r from the target antenna. So I'll again pause over. In the previous slide, we saw the sorry Friss equation. Now we have seen the radar equation. So I'll pause over here. If you have any questions on this, about the steps that we went through. So it's all based on what we have seen in the previous classes as well. Okay, so if there are no questions on this, we'll continue. So let's solve a problem based on the phase transmission and radar equation. Okay, so we have this example from the textbook where we have that we have to we are given that given that 50 kilowatt of power is fed into the antenna of the radar system operating at 3 gigahertz. So we are given the amount of transmitted power. We are given the frequency, which implies we are given the wavelength. The antenna has an effective area of 4 meters square. So we have also been given the effective area. The radiation efficiency of 90%. So again, this implies that this is not the transmitted power. You have to take the 90% of the power which is fed to calculate the transmitted power. The minimum detectable signal power over noise inherent in the receiving system from the environment is 1.5 picowatt. So so this in this case the receiver must receive 1.5 picowatt of power, and the power reflection coefficient of the antenna, the receiving antenna, is 0.05. So we have some mismatch as well. There's some mismatch as well. Uh, Determine the maximum usable range of the radar for detecting a target with backscatter cross section of 1 meter square. And now we have the sigma backscatter as well. So let's start solving this. So at for 3 gigahertz, we have lambda as 1 meter, zero point 0.1 meter. We have the effective area. The transmit power is 90% of 5 kilowatt, which is 4.5 kilowatt. We're given the received the minimum power that has to be received at the load is 1.5 picowatt. But again, there is some mismatch at the load, so we have to take into consideration that as well. So we are given that the power reflection coefficient is 0.15. So uh, if we send 1 watt of power, um, it will reflect back 0.05 into 1 watt of power back to the source, and uh, we will receive 0.95 watts. Okay, so if we are sending x watts of power, it implies it will reflect like 0.05x, and we will receive 0.95x. So it implies that if we want to receive yeah, the x amount of power over here, we have to if we want to receive x power over here with it, we have to send x by 0.95. So that's what we have done over here. 1 upon 1 minus 0.5, 0.05. This implies the minimum power that should be received is 1.58 to 10 power minus 12 watts, 1.58 picowatts, and we have the sigma backscatter as 1 meter square. Using which expression should we use? So we have AE, PT, PL, and sigma BS. So we'll use this expression. We have PL, we have PT, we have sigma BS, we have AE, and we need to find out the distance. Determine the maximum usable range of the radar. So we have to calculate the range of the radar. So rearranging this expression, we'll have R bar 4 on the let's say left hand side, and bringing all other terms to the right hand side, we have sigma bs a square 4 pi lambda square and pt upon pl. Substituting all the information from here and then taking over, if we remove this 4, we have to calculate the fourth root. um, Use a calculator and you'll get this expression 4.36 into 10 power minus 4 meter, which means the range of the radar is 4.36 kilometer. So I'll pause over here and take any questions that you have on this example. Okay, so I guess no questions. It was pretty straightforward. Like the only confusing part was that I found was this thing where you need to calculate the correct amount of power which has to be received at the load, because we have some mismatch. But we did that and then calculated the radar range. Now, some this is like a trivia. So this radar range equation and the phase transmission equation are very frequently used in satellites where you have uh, some transmitter over here and there is another there's some receiver over here, or you want to communicate with the satellite. So you send in signal to the satellite and it receives and then it uh, and so you send the signal to the satellite, it receives the signal and then amplifies it and then sends it back. So, and then there are two types of satellites as well. There's this geosynchronous satellite which goes around the poles, uh, and then there is this geostationary satellite which goes around the orbit such that it always appears to be stationary. For example, if this geostationary satellite has the same orbital velocity and same as the Earth, or so the total period time for its revolution is same as the Earth's rotation. So for an object which is on Earth, it will always appear to be stationary at one point. And we typically have three of these to cover the entire Earth. For example, if there is a transmitter over here and we want to receive it on some other side of the globe, so it can send the signal to one of the satellites, and which can, if the satellite if this first satellite can communicate with the receiver, it's solid. Otherwise it will send it to some other satellite and then it will come back, or it will send it to some other station on the ground and it will then send it back to another satellite. So it could be any of this way. So this is about one of the famous applications of the radar range and the Friss equation. So you can read this text which is there in the textbook as well. And we have these two kinds of satellites around the Earth's orbit. So that's it for the Friss transmission and formula and the radar range equation. We'll now quickly discuss the wave propagation near Earth's surface, because the Earth's surface reflects back the EM waves uh, from the surface. So you don't when you transmit a signal, it does not mean it means that uh, it it can either travel in the line of sight, and it can also use this path where it reflects back from the Earth's surface and communicates. So, well, it was some observed some point that even if your transmitter does not have a line of sight view to your uh, uh, receiver, it can still you can still communicate within the two devices by the reflections from the Earth's surface and your atmosphere. You have your ionosphere over here, so it can transmit, it can communicate like this as well, something like this. So so there will be multi-path as well. So we will take a very simple case when you have your transmitter and receiver in the line of sight, but we also have the Earth for reflection. So what is the correct amount of power and the electric field which is received? So we're considering a transmitting antenna A over here, and it is at a height h1, and there is a receiving antenna B over here, and it is at height h2, and they are at a separation of D. So if antenna A is an elemental electric dipole, uh, then the electric field intensity at B is the sum of the direct contribution E01. So this is the direct contribution through path R, and this is E01, and then indirect contribution E02 through the reflection through the Earth surface after reflection from point C over here. So we can write the total electric field received as the sum of the direct and indirect electric field due to the direct and indirect path. And the magnitude of the direct path is k times e power j beta r by r. And the indirect path is and sine theta as well, because yeah, sine theta, and E02 as is k times e power minus j beta r dash by r dash sine theta dash. Okay. Um, so the contribution can also be so in this case, since this is an elemental dipole, we can, and this is the Earth surface. What we are doing is we are uh, taking the it's this can very well be taken as PEC, and then we can take its image over here. And once we take the image, we have this theta dash is the angle, and a dash we take considering this a dash antenna, and this is the h1 height between the from the surface. So we have so this acts like there are two sources which are so it will appear like that at point B. And the constant is can be given as Ji dl n naught beta 1/4 pi. So all this is from the derivation of elemental uh, electric dipole, which we did in the initial classes. And the distance r dash can be calculated as the distance between AC, this is the AC, and distance CB. And this final distance can also be written equal to distance between A dash and B. So distance between A dash B. Now, okay, let me just clear this. Start again from this slide. Okay, so we can write the total electric field over here as sum of E01 and E02, when E01 is due to the direct path and E02 is due to the indirect path. And for the antenna A, we have taken its image over here because the ground acts as PEC, and it will be at the same distance from this ground surface, and this A antenna makes an angle of theta dash. And from the previous knowledge, we can write the electric fields like this. And the r dash distance is basically this a dash into a dash b is the distance, which can be also given as the sum of AC plus CB. Now the effect of perfectly conducting azure surface is replaced by this image antenna a dash over here. And in general case, these electric fields E01 and E02 will are not parallel, but for large distances. So this considering this D is much greater than this H. So these two lines can also be considered parallel, and hence these electric fields they will be parallel. And in that case, we can directly add them. This is an approximation we are doing to simplify our lives. And in that case also, this when these lines become parallel, this theta dash and theta, they will also be considered parallel. So doing this approximation, we can write the final electric field E theta is equals to k times e power minus j beta r into by r and sine theta and f. But this f factor is basically this r dash thing over here. So this is 1 plus e minus j beta r r dash minus r. Now, since this r dash minus r, this if this was outside over here, we can just approximate r is very close to r dash. But if it is in phase, in that case, we cannot ignore it. We have to do a better approximation. So up till now, what we did was we can give the electric field as sum of the individual electric field with principle of superposition from the two paths. Individually, the fields can be written like this, and considering both these paths to be parallel for large D, we can write the electric field like this, where this F is given as this expression. Now, this doing a better approximation for R dash minus R. So R distance is this R distance can be written as D square. Okay, so consider this triangle like this, right? So this is the distance D, and this particular distance is H2 minus H1. So by using Pythagoras, we can write this expression, and then using binomial expansion, we have r is equals to d plus h2 minus h1 square by 2d. Similarly, r dash can be given as d square plus h2 plus h1 square. So this is r dash, right? So this r dash is this big triangle. This is, and this triangle has this base as d, and this is h1 plus h2. So this entire thing is h1 plus h2, and hence by using binomial expansion, we can write it like this: d plus h2 plus h1 whole square by 2d. And now calculating r dash minus r, we can write it as this expression calc, and this simplifies to 2 h1 h2 by d. So we have r dash minus r now. Using this expression inside 1 139, we have 1 plus e minus j beta 2h1 h2 by d. So this is all math. So now we have got this expression for f. Now using this and this basically resembles the array factor which we had seen earlier, which is like a array factor of two element array. And now this can be rearranged to give this expression 2 cos 2 pi h1 h2 by lambda d. Now for constant h1. So for example, if this is our tower, so this tower height will let's say we have build a tower of h1 height, and we are keep operating at lambda frequency, at lambda wavelength, which implies like constant frequency f. So in this case, this implies that for fixed values of h1 and lambda, the electric field intensity at the receiving side B will have nulls and maximum values based on the ratio H2 by D. So this height of the receiver and this distance, based on these factors, we can have a very we can have either very low electric field or very high electric field, which it can be seen from this expression. So this makes sense when at some positions where we have good signal reception, but in some others positions we have bad signal reception. And this quantity f mod f can vary between 0 to 2 and is called the path gain factor. So this is another term you will want to remember, path gain factor. And calculation of the path gain factor for for spherical earth involves a much more involved task. So this was all very simple if this is a flat surface, but if it is spherical, we'll have to do better approximations. So that's it for today. In the next class, we'll do some other types of antennas. Um, we'll see. So just pause over here. We did a lot of math starting from this figure, the expression for electric field at different steps, calculating the difference value for the phase part of the array factor, which like array factor like term over here, and then this observation from this expression that we will have nulls or maximas in the path from the at the if the receiver is moved from one from the distance from the transmitter. So I'll pause over here. If there are any questions on this, we can take them now from here or the previous slides. Else we can end this meeting. Okay, so if there are no further questions on this, I'll share the slides. You can go through these steps in more detail. And then if there are any questions, you can get back to me or by email or through the WhatsApp group um, or DMs. Okay, so we'll stop now.